we're Team ABCA, and we would like to present our approach to the topic of to design a human body temperature detection sensor using basic circuitry. Hope you enjoy it. Type of thermistors. Starting with the basic fundamentals, thermistors are instruments where the resistance changes along the temperature being detected. NTC thermistor, aka negative temperature coefficient thermometer, has decreasing resistance with increasing temperature, whereas PTC thermistors, aka positive temperature coefficient thermometers, have resistance rising abruptly at around 100 to 150 degrees Celsius, which is not the region of temperature we will be detecting. An alternative is to use a thermocouple, which is designed to output voltage that depends on temperature.
Advantages of NTC thermistors over the remains. Looking at the graph, the NTC thermistor has the greatest change in resistance in the region where human body temperature lies. This is a benefit since it means the instrument will be more sensitive than the other instruments. Thermocouples are more expensive and slower in response time when compared to NTC thermistors.
This is our precision circuit. The three types of circuits were integrated to design and construct a more precise and accurate circuit. On the left we have our potential divider circuit, on the middle is our differential amplifier circuit, and on the right is the non-inverting amplifier circuit. V-in, V-out, and ground are all connected to the Arduino microprocessor. We will discuss the further details of our circuit.
We have used a voltage regulator that stabilizes the voltage supplied to a potentiometer circuit. This allows us to keep the voltage at 5 volt, enhancing the accuracy of the potential divider circuit. This is because the final voltage that will be fed up to our Arduino board will fluctuate less due to our stable source.
The potential divider circuit is designed to divide the voltage from a voltage regulator according to the two resistance value from a fixed resistor and NTC thermistor.
Right, so potential divider circuit number 1. Along our thermistor, we have chosen to use a 6200 ohm resistor which maximizes the range of the VF. This is shown by the following table on the presentation. Over to slide number 8, potential divider circuit number 2. This potential divider circuit is used to be able to extract the perfect potential difference value which will be used in the differential amplifier circuit. When having an almost equal value of potential difference up to the VF we have extracted from the previous potential divider circuit, we were able to bring the range of our potential difference value fed to the non-inverting amplifier as close to 0. We will explain the benefits of the following in the later on.
Onto the differential amplifier. A differential amplifier uses an operational amplifier in the circuit used to output the potential difference between two lines of current. Here, we're using it to maximize the range of inputs into the Arduino microprocessor. The range of voltage for our thermistor is 2.3 to 2.8 volts, which means that it has an effective range of 0 to 0.5 volts. By lowering the voltage to as close as that range as possible via the differential amplifier, and then using a non-inverting amplifier to amplify the voltage, we can utilize the full range of inputs acceptable to the Arduino board from 0 to 5 volts, which results in greater precision. Here's the proof behind how the differential amplifier works. So just take a moment to look at that.
The non-inverting amplifier uses an operational amplifier in the circuit. After bringing the minimum of the range as close to 0, the non-inverting amplifier will multiply the following potential difference with the gain to increase the range of the voltage values read by the Arduino board to 0 to 5 volts. The formula for getting a value for gain is 1 plus R1 divided by R2. This is necessary to be able to use the fullest potential of the Arduino board capable of reading values from 0 to 5 volts. The proof of the operation of the non-inverting amplifier has been given.
We can see that the final voltage measured by the Arduino will vary from 0 to 5 volts. This means that we are using the fullest capability of the Arduino board, which is capable of reading voltages from 0 to 5 volts.
Tolerance. Tolerance is the percentage error of resistance in the resistor. To create a precision circuit, we purchased resistors with ±1% tolerance, boosting the precision of voltage value read by the Arduino at certain temperature.
Colored bands on resistors. We can identify our fixed resistor tolerance by looking at the band. Looking at the diagram, the first 3 bands represent resistance, 4th band represents multiplier, and the 5th band represents tolerance. Our resistors have a brown 5th band representing a 1% tolerance in resistance.
The following image shows that we have created a fully functional thermometer with a display, which means if an analog signal is detected on the Arduino, the temperature can be calculated using that reading and displayed.
Right, so assumptions that we made. The following are the assumptions we made when using the non-inverting amplifier. Firstly, we assumed that the operational amplifiers we used had infinite impedance, zero output impedance, and zero noise. However, the op-amps will have limited impedance and little noise, while the Arduino will draw a small amount of current. We also assumed that the wires in the breadboard and the jumper wires had zero resistance. As some wires were not soldered, we knew there were small amounts of contact resistance between the breadboard and the jumper wires. Although these changes are small and negligible, they might become a noticeable source of error in our readings due to precision.
So the issues we faced while building a physical thermometer. Firstly, current was able to flow backwards in the circuit where it shouldn't have. Therefore, we've installed diodes to prevent the backwards flow of current in our physical circuit. Secondly, the two 47 ohm resistors were meant to act as a potential divider for the input of the differential amplifier. However, it ended up making a parallel circuit with the thermistor, therefore reducing its resistance and hence charging VF. Therefore, we have replaced the two resistors with 1 million ohm resistors so that the effect of the potential divider on the thermistor will become negligible.
Applications to the real world. Thermometers are currently being used in countless of industries.
By adjusting the values of some resistors in our precision circuit, we were capable of shifting the range of temperatures the precision thermometers could detect. This enables our circuit design to benefit not only in medical factors, as measuring temperature of human body was the main objective in this project, but also in industries such as the production of semiconductors, farming industries, and etc.
Probe thermometers are easily one of the most common types of thermometer. They deliver instant temperature readings of foods, liquids, and semi-solid samples. The probe is often equipped with a pointed tip, making them ideal for penetration and immersion. They are ideal for their use in the catering trade, for hygiene testing, retail outlets, and laboratories. Alarms, folding designs, and a whole heap of features are available. If being used in a professional environment, traceable calibration is the strength of this instrument.
Temperature data loggers allow the recording of continuous temperature measurements. Once activated, they record the temperature at predetermined intervals and save it into memory. It is typical to download the data and view it on the graph, but some devices display the data in real time. Most devices are compatible with any PC, laptop, or tablet. Their design allows them to track heat levels in critical areas where a constant temperature must exist. Common places to find them include storage room, transportation, and laboratories. Types of thermometers that perform critical roles such as this should always be calibrated. Since our circuit has a built-in microprocessor that can be attached to a device, we are able to use our circuit as a temperature data logger.
A specific example of where precision thermometers are required. Semiconductors have a negative temperature coefficient for resistance. This means that conductance increases and resistance decreases when heated. Heat applied to semiconductor material causes the separation of the outermost electrons from the atom, atomic nucleus of the material compounds due to an increase in energy. These free electrons become conductive. As the number of free electrons increase, there will be an associated drop in resistance. Maintaining temperatures within a specific range is necessary to facilitate the proper function of electronic devices that operate using semiconductors. Tightly regulated temperature control is even more critical in semiconductor manufacturing.
Enhancing the accuracy of a thermometer. Even if the most precise thermometer was to be built, a more accurate thermometer brings more benefits. This is where calibration comes in. Finding a suitable method to calibrate such a sensitive device is crucial and influences the performance of the instrument. Calibrating a device may be able to cancel out inaccuracy caused by zero error of instruments.
Calibration. One way to calibrate the instrument is by using the 0 degrees Celsius point by utilizing the characteristics of water. By producing an iced water bucket, we are able to produce a stable 0 degrees Celsius point. In this progress, giving enough time for the thermistor to sense the environment fully will help boost the accuracy of such a device. You can use this method not only to calibrate your device, but also to check if the device is properly functioning. Since water changes phase at 0 degrees, which is not a temperature our thermometer is designed to measure, we could use a liquid substance called dimethyl sulfide, which has a boiling point of 37.3 degrees Celsius to calibrate our specific device. Since dimethyl sulfide is flammable, this will be done in a water bath of a temperature of around 60 degrees Celsius. Hope you enjoyed our presentation.